For IB chemistry, you have to know several trends in the periodic table, as well as important properties of specific groups in the periodic table. So to begin with, we'll introduce the various groups, namely the alkali metals, the alkaline earth metals, the halogens, the noble gases, and the transition metals. Those are the ones that you might already know. The ones that might be new to you are the lanthanoids and the actinoids, which are, helpfully, named after the first elements in their respective groups. So now that we've cleared that up, we can begin to look at some of the trends. Trends in atomic radii, electronegativity, electron affinity, and ionic radii across a period and down a group. So what's the trend in atomic radii? Well, across a period, atomic radii decreases, and down a group, it increases. It's possible that the first claim I made seems a little bit counterintuitive. So, what's the explanation? Put simply, as you move across a period, the number of protons in the nucleus is increasing, meaning the forces of attraction that the atom is exerting on its outer shell is increasing, pulling the electrons in, thereby decreasing the atomic radii. Conversely, down a group, the forces of attraction exerted on the atom's outer shell decreases because of the added shell on each element, increasing the distance from the nucleus. Secondly, electronegativity. Well, electronegativity is the attraction between the nucleus and the bonded pair of electrons in a covalent bond. That's crucial. You can only measure electronegativity in a covalent bond. Basically, it's a measure of how easily an element keeps its electrons, gains electrons, and pulls them close, and is related to the property of some compounds where each side has an opposite charge. So what's its trend? Well, I'm quite sure that you can actually work it out based off the trends in atomic radii and your excellent understanding of metals and nonmetals. If across a period the atomic radii decreases, then that means that the nucleus is able to exert a higher force of attraction on its electrons, and so, of course, electronegativity increases across a period. Similarly, down a group, the atomic radii increases, so the electronegativity decreases. Why did I mention metals and nonmetals? Well, you also have to know the general trend across the whole periodic table. That is that the lowest electronegativity is found at the bottom of the alkali metals, francium, and the highest with fluorine at the top of the halogens. This makes sense, right? Because francium is a reactive metal that easily loses electrons, and fluorine is a reactive nonmetal that easily gains electrons. Alright, so we're moving quickly through these, and now we're on electron affinity. The name is in part deceiving because you're going to have to learn the definition, and it doesn't exactly seem to have anything to do with affinity. So the definition is the energy change when 1 mole of gaseous negative ions are formed from 1 mole of gaseous atoms and 1 mole of electrons. You're going to have to learn that, but it's perhaps clearer if we look at it in the form of an equation. So, as you can see, the element, and it doesn't matter whether it's a nonmetal or a metal, is gaining an electron and forming a negative ion, and this releases energy. That is to say, it's a exothermic reaction. So what's the trend? Well, first, a disclaimer. This is a pretty rough trend, but anyways, across a period, the energy released increases, and down a group, the energy released decreases. Why is this? Well, we can once again link it back to atomic radii. The smaller the atomic radius, the greater the force of attraction on any nearby electrons, and so the more energy released when an electron is added. Arguably a bit hand-wavy, but it's all you need to know for now. One exception that's pretty fun is in the halogens. You'd expect fluorine to have the highest electron affinity, but instead chlorine does. This is because of the fact that fluorine is such a small atom that its electron density is so high that the adding of an electron is significantly affected by the repulsion between electrons, and so more energy needs to be inputted in order for the reaction to occur than with chlorine. So overall, less energy is released. Finally, ionic radius. This is definitely less of a trend and more of a general statement, but you do have to know it anyways. So basically, When an element becomes a positive ion, its radius becomes smaller, and when an element becomes a negative ion, its radius increases. Both of these can be explained by the fact that electrons repel each other. So if we take an element X, and in this case it'll generally be a metal, and it loses an electron, that means that there's less repulsion between them, these remaining electrons, and so the electrons can get a bit closer together without being unstable. And then if we take element X again, but this time it'll generally be a nonmetal, and you imagine it gaining an electron, there's more repulsion between the outer shell electrons, so they need to space out a bit in order to return to a more stable state. I did say finally, because that is it for this video, but you also have to know about trends in melting point and boiling point, reactivity, and things like density and color, as well as some of the specific reactions with halogens and properties of transition metals, all of which are covered in my video for IGCSE students, but it is material that you do need to still know, so feel free to check that out, and thank you for watching.